If you're the pilot of one of the Navy's strong arms, an attack aircraft of any type, and we get into a fight, you can expect to face two conditions. The first is that when you are attacking the enemy, he will be attacking you with every means at his command. And second, his weapons and equipment may be as good as ours. To be specific, if your mission takes you to a typical enemy target area, what defenses can you expect to find? Well, we know from our intelligence reports that the enemy has interceptor aircraft, all weather as well as day types, that he has missiles, surface to air and air to air, and that he has anti-aircraft guns. We also know that these weapons are parts of integrated automatic systems controlled by various types of radars. Among them are early warning radars operating at low frequencies. He has GCI radars, ground control intercept, for acquiring and tracking us, and for controlling his interceptors. And he has fire control radars for controlling his missiles and guns. Then there is a radio communication net that ties the complex together and transmits information and orders to the interceptors. In spite of what we may know, each particular target area will raise questions when a mission is planned. In the first place, how will you get through to the prime target and deliver the weapon? Can you deliver a second one? And how will you get out? How can you increase your chances of survival? First, of course, is to choose a route that minimizes the risk, and if possible, take the low road, down where the ground-based radars are less efficient. And use electronic countermeasures. For example, you might jam the enemy's radars with the brute force method. One drawback, however, is that such a signal reveals your position. Also, it could provide a perfect path for homing missiles. More advanced countermeasure concepts are embodied in DECM, Defensive Electronic Countermeasures, the invisible shield that you carry, so to speak, along with your sword. One of these countermeasures, the AN-ALQ-35, is a multiple target repeater. It confuses the enemy by painting false returns on his PPI scopes so that he is unable to distinguish the true returns. Another is the AN-ALQ-55, a communications countermeasure. It disrupts the enemy's radio link to his interceptors, denying them the data they must have to find you and fire at you. The third type, the AN-ALQ-41 and the similar 51, is track braking. It protects your aircraft by breaking the enemy's lock-on or by giving him false information about you. DECM, then, provides electronic countermeasures that confuse, frustrate, and deceive the enemy, thereby delaying him and buying time for you. Minutes of immunity that can spell success for the mission and survival for you. The Navy has installed defensive electronic countermeasure sets in three types of attack aircraft. The A2F is equipped with the track breakers, one ALQ-41 located aft and operating in the X-band, which is most often associated with airborne radars, and two 51s, one forward and one aft, operating in the S-band, which is most often associated with ground-based radars. The antennas are located inboard and outboard of the jet air intakes and in the vertical stabilizer. The A3J carries one ALQ-41 and one 51, with the antennas providing coverage at high and low altitudes. In addition, the A3J has an ALQ-55 communications countermeasure set. Its omnidirectional antenna is on the nose wheel door. The A3D aircraft has sufficient space and weight capacity to enable it to carry all DECM sets, an ALQ-35 multiple target repeater, an ALQ-55 communications countermeasure set, 2 41 track breakers, one forward and one aft, and 2 51 track breakers, one forward and one aft. The antennas are located at various positions in the airframe. It is our purpose in this film to show the general principles of operation of each of these countermeasure sets. The multiple target repeater set, as we have noted, affects the enemy's PPI scopes. It paints false returns, covering a narrow angle during the early approach, then progressively increasing it, eventually covering the entire circle. The radar operator knows he is being deceived, but you are a needle in a haystack to him. To see how the display is created, let's begin with this plan view of the radiation pattern of an enemy radar, say a GCI search type. Let's assume that you are within his range. Although energy is transmitted by all lobes, for clarity we will show only the radiation in the direction of the aircraft. When the radar transmits a pulse, your skin return appears on his PPI scope. Your ALQ-35 receives each pulse, greatly amplifies it, and after a short delay, repeats the signal. That is, transmits it back to the radar. As a result, a false target appears on his scope. It is farther out than the skin return because it was received later, due to the delay. The succeeding pulses are repeated, but with random delay times, so that many false targets appear on the scope. Some of these appear at shorter ranges because they have been delayed long enough so that each appears to be the echo of a succeeding pulse. The radar, of course, rotates. Let's see what the effect is. As the main lobe leaves the target, the side lobe energy is too weak to produce a skin return that can be detected by the radar. However, the sensitive ALQ-35 detects each pulse of this side lobe energy and repeats it. As a result, the radar receives false returns through this angle of sweep, and his scope displays them. Consequently, the enemy does not know where you are, nor does he know how many aircraft are being detected. The side lobe energy may decrease to such an extent that the ALQ-35 cannot detect or repeat it. But false returns will again appear when the radar presents a strong side lobe to the 35 receiver. As the target gets closer to the radar, the false target area widens, and the 35 picks up more and more of the side and back energy. Ultimately, the entire circle may be covered, and it is virtually impossible for the enemy to find the weak true returns that would reveal your position. When you first approach the enemy, you will enter the zone in which your ALQ-35 can receive the enemy's radar pulses, but he cannot detect your skin return. When the main lobe sweeps in your direction, you receive him through this small angle. If you were to turn on your transmitter and repeat his pulses here, he could spot your bearing by that small angle. To avoid this, you wait until you are closer and the angle widens. The wider, the better. Just before you reach the point where he will detect your skin return, a point determined by intelligence reports or by your other DECM sets, you turn on your transmitter and begin repeating. The relatively wide angle spread of false targets makes it more difficult for him to find you. You should not turn on your repeater before the optimum time. Once you are within his range, he will get a skin return, but will have a difficult time finding it. This radiation pattern is a rather simple one. You may run into more complex types, such as the token radar. Its 5 beams operate at different frequencies. While the frequency of one of the beams is too low to be received by the ALQ-35, the others can be received and repeated. In certain target areas, your set may have to repeat several radars simultaneously, thus dividing your power output. On the other hand, a number of aircraft operating together will multiply the DECM output, increasing its effectiveness. The set's hardware comprises 4 major components: the radio frequency tuner, the pulse generator, the transmitter, and the control. A receiving and a transmitting antenna are used with the set. The tuner contains the receiver portion of the set. It operates in selected sections of the spectrum between 2,000 and 4,000 megacycles. The receiver employs 10 plug-in channel filters. Each covers 50 megacycles. In all, 40 filters are supplied with the set. Of the 40 channels available, any 10 can be selected, singly or in groups, the choice being based on intelligence reports of the enemy's operation. Since each filter covers 50 megacycles, a total of 500 megacycles will be covered. The tuner triggers the pulse generator, which in turn generates a randomly delayed pulse to the transmitter for amplification and transmission as a false target signal. An important feature of this and the other DECM equipment is the use of traveling wave tubes. Operating wide open as to frequency, they accommodate all signals throughout the band without tuning. The transmitter output tube furnishes a peak pulse power of about 1 kilowatt. The control is used to set the modes of operation. Turning the switch to standby warms up the equipment, with the light indicating readiness. In receive, the set will operate only to receive radar pulses. When the light goes on, it indicates that your aircraft is being illuminated by a radar. The repeat mode puts the transmitter into operation. It operates only during the time a radar signal is being received. The ALQ-35 countermeasure set is a valuable shield. By causing confusion, it buys time. Time that can save lives. Let us turn now to the communications countermeasure set. Its function, you'll recall, is to disrupt the enemy's radio link to his interceptors. Let's see how the set operates using a diagrammatic representation. The set covers the 100 to 210 megacycle portion of the VHF band of radio frequencies. GCI, ground control intercept communications, are in the form of frequency modulated CW for voice and data link signals for data transmission. These are the enemy communication signals to be disrupted without wasting countermeasure energy on other VHF signals such as TV, ground-controlled approach, amateur, marker beacon, carrier-controlled approach, and FM broadcasting. The ALQ-55 can distinguish one type of signal from another by means of identification circuits, with a memory device storing the data. In operation, the set scans the spectrum, searching for signals. When signals are detected, the receiver evaluates them. If a particular signal is classified as a threat, the set transmits an appropriate jamming signal on that frequency. The transmitter operates only during signal reception. Since the jamming signal is not continuous, the enemy cannot use it to detect you or home on you. At least 6 signals can be handled simultaneously, and as many as 20 could be jammed with a reasonable degree of effectiveness, depending on their interrelationship. The major components are The receiver modulator, a multi-channel device that employs 6 receivers that operate simultaneously and in parallel, the receiver power supply, the transmitter with an average output power of 500 watts and a peak of 1,000 watts, the transmitter power supply, and the control. The system uses a single omnidirectional antenna with a duplexer. The components are mounted on a shock-protected rack. The receiver modulator and its power supply, the transmitter and its power supply, and the control. The control resembles that used with the ALQ-35. A self-test button is provided. Standby is the warm-up setting. Receiver is used for listen and transmission. The transmitter is turned on by a separate guarded switch. An override setting permits battle short operation in an emergency when it may be necessary to override all thermal and electrical safety devices in the set. The ALQ-55 is an effective countermeasure set. Its use calls for careful planning, judgment, and timing in order to achieve the objective of the mission. Now let's see how the track breakers operate. While the 41 and the 51 differ somewhat in physical makeup, they perform the same function: to break lock-on and to give false information to the tracking radars. These radars employ various techniques for tracking targets in angle and range. Pulse ranging, which uses a range gate. FMCW, which uses a Doppler speed gate. Conical scanning, which nutates the beam about the target. And monopulse, which uses a single pulse and a beam divided into 4 quadrants. The 41 and 51 sets are effective against all 4 of these and can handle them simultaneously by means of built-in programmers. In a pulse-ranging radar, the beam is locked onto the target by means of a range gate. As the target changes range, either in closing or opening, the range gate moves with it. Like the ALQ-35, the 41 and the 51 are designed to receive radar pulses, amplify them greatly, delay them, and repeat them. That is, transmit a simulated echo back to the radar. This return is far stronger than the true return, and it captures the range gate, gradually pulling it away until the gate is no longer on the target. The set then suddenly stops transmitting false returns, and the radar finds itself without a target. Lock-on is thus broken, and the enemy must resume searching for you, losing valuable time that you gain. Although the radar may reacquire you, the 41 and 51 again begin the process of breaking lock-on and transmitting false information. You are being protected by your DECM shield. Now let's see how FMCW tracking is broken. When the transmitted beam is reflected from a moving target, the return signal will have a different frequency due to the relative motion of the target and the radar. The frequency difference is the Doppler frequency, which the enemy measures by means of a so-called speed gate to determine your speed. To disrupt the speed determination, the countermeasure set in the aircraft receives the radar's transmitted signal, greatly amplifies it, and repeats it as a simulated return. The set gradually increases the frequency of its repeat signal. Then it suddenly causes an almost instantaneous flyback to the original frequency and proceeds to decrease the frequency with another flyback. To the radar, it appears that the aircraft is undergoing impossible maneuvers, instantaneous changes of speed, and rapid accelerations and decelerations. Consequently, the speed gate cannot function properly, and tracking is disrupted. The result is a useless, interrupted flow of data to the enemy's fire control system. In conical scanning radar, the beam is nutated about the target. If the beam is off position, the return pulse train will be amplitude modulated. The modulation envelope is used to make corrections in the beam's azimuth and elevation, positioning it back on target. The countermeasure set throws the beam off target by a scan inversion technique. The 41 or 51 system detects the modulation envelope. The signal is then amplified and inverted. This simulated modulation envelope is transmitted to the radar. Based on this simulated envelope, the radar's angle tracking circuits make beam corrections in the opposite direction to what they should, thus driving the beam further away from the target instead of toward it. Thus, scan inversion breaks angle lock-on, and the radar reverts to search mode. Now, what about monopulse? How is this tracking technique disrupted? The monopulse principle, very briefly, is based on the use of a single polarized pulse of RF energy. It is reflected from the target and returns to the radar through a 4-quadrant receiving horn. If the beam is off the target, there will be phase and amplitude differences in the quadrants, and these are used to reposition the beam. To break lock-on, the set receives the polarized signal, amplifies it, and cross-polarizes it in a sequence of circular, vertical, and horizontal polarizations. The cross-polarized return signal causes erroneous corrections to be made in the beam's position, and it spirals away from the target. This, then, is the fourth achievement in deceit produced by the ALQ 41 and 51 DECMs. The hardware for the 41 consists of the receiver, the transmitter, the control, and the power supply. A receiving and a transmitting antenna are used with the set. The set covers the X-band, the frequencies from 8,000 megacycles to 12,000 megacycles. As in the 35, traveling wave tubes are used, and the set is able to respond simultaneously to 20 or more radars. The hardware for the ALQ 51 consists of just two components: the 1,000-watt peak power receiver transmitter and the control. The 51 operates in the S-band, 2,000 to 4,000 megacycles. The control unit is similar to those of the other systems. In these defensive electronic countermeasures, then, you have equipment to cope with the enemy's defense systems. The AN-ALQ 35 confuses the enemy by painting his scopes with countless false targets, making the task of finding you difficult, to say the least. The ALQ 55 disrupts his communications, denying vectoring information to his interceptors, thus frustrating his most effective weapons. And the 41 and 51, by breaking lock-on and giving him false and interrupted data, degrade his effectiveness and reduce him to visual and manual operation of his equipment. You gain your greatest ally, time. Field tests and studies have shown that the use of these countermeasures will reduce the effectiveness of interceptor action by 2/3, and that of anti-aircraft guns by 7/8. But maximum effectiveness will be achieved only after study and training have given you familiarity with the operation of DECM equipment and a sound understanding of its capabilities and limitations. Defensive electronic countermeasures, your best and sometimes your only protection against modern automatic weapons, will help you make your strike and bring you home again.